All right, so this video is going to be a little on two sections for chapter 3, section 3.4 and 3.5. 3.4 deals with the motion on a ramp, and we're going to look at how a ramp changes the motion of an object and how the acceleration due to gravity is affected by the ramp. All right, so something slides down a ramp, okay, if it's tilted at an angle, and both the acceleration and velocity vectors are parallel to your ramp. So you have the object is going down the ramp, assuming there's an angle of incline here. Okay. Notice it accelerates up, but it's as it goes down the ramp, its acceleration is constant, so its velocity is increasing at a constant rate. All right, so here's the math portion of the ramp piece. Okay. Acceleration due to gravity is always pointing straight down. Okay. But now there's going to be two components to make up this free fall acceleration. There's an x component and a y component, which actually make a right angle to each other. So the x and the y are components of the free acceleration to free fall. And this free fall acceleration is constant. Okay? So that means as this angle of elevation changes, so does the angle between the free fall and the y component of your acceleration. Okay? So you can kind of think about it is if this angle gets bigger, so does this, which actually means that our x component of acceleration increases, which means it's going to go faster down the hill. Okay. So when we're looking for the x component of the acceleration, you can think of it using SOHCAHTOA, use the trig functions. We're looking for the opposite side, and we have the hypotenuse. Okay, so opposite side is sine of the angle times g gets you the acceleration downward. And you can see as if g is constant, as the angle gets bigger, so does your x acceleration. All right. Okay, sample problem. Okay, we're looking at skiers going down a hill. All right. During this acceleration phase, the skiers traveled 360 meters while dropping a vertical distance of 170 meters. We're looking at what's the fastest speed a skier could achieve at this run, at the end of this run. So, when we look at this, we have to set up a problem here. We know that they're speeding up as they go down the hill. We know the slope length is 360 meters. We know the height is 170. So because we know the slope and we know the height, we can figure out this angle of elevation here. Okay. And if we know the angle of elevation, then we can figure out the acceleration rate. Then we can figure out V final using your kinematics equations because our acceleration is constant. Okay, so we're going to use sine. Okay, because we know the opposite side and the hypotenuse, so we're going to figure out the sine of theta equals opposite 170 divided by 360. So when you do that, theta is equal to the inverse sine of 170 over 360, which is 28 degrees. Okay, so we know our angle now. Now we can figure out what the acceleration is down the ramp. We take our angle, take the sine of the angle times g because of this formula which was given to you at the beginning of this presentation. That'll get you your acceleration parallel to the ramp, which is 4.6 meters per second squared. So now we know the acceleration. We know the distance, the length of the slope. We can figure out the final speed because of this initial kinematics equation. Our initial speed was 0. We know A. We solved for that in the previous slide. X is 360. We can solve for VF. Okay. So this is the fastest speed on that ramp that anyone can go. Now, obviously, like it says here, friction and air resistance are going to decrease it. So if you know an angle and you know the length of a ramp that something's going down, you can very easily figure out how fast it could possibly go down that ramp. Okay? All by using the kinematics equations. Okay? So that's about 130 miles an hour. Okay? It didn't work. The reality of it is it only got to 111, but that's due to friction and air resistance. Okay, that's the end of the first of 3.4. 3.5 deals with relative motion and looking at how motion compares to different points of view. All right, so we've got these three people watching this runner. Amy standing still, Carlos going in a car of 15 meters per second, Bill on a bicycle going 5 meters per second. And we're going to see how they see this runner moving differently depending on their point of view. Okay. So first of all, relative to Amy, the runner looks like they're going 5 meters per second away from Amy. Okay. From Amy's point of view, Carlos is going 15 meters per second. The runner is going 5 meters per second. The bike's going 5 meters per second. Okay. And we have this equation. So we have relative to Amy is RA, CA is Carlos relative to Amy. So we're looking for the relative speed. Which means then, if you can kind of think about it, from Bill's point of view, the runner looks like he's going at the same speed as Bill because he is. Okay. From Carlos, the runner looks like it's actually the runner's getting farther and farther away because Carlos is going 15 meters per second where the runner's only going 5. Okay. We're also going to look at this, the idea of flight speed, and adding speed vectors together to get a true speed. It's kind of like if you think about going against or with the wind. Okay. So we're looking for the airspeed relative to the air. We know these velocities. We know that as the bird is observed maintaining this sustained flight of 35 meters per second. Okay, and find the wind was going 23 meters per second. So we're looking at what's the bird's airspeed, its speed relative to the air. Okay, so we know that they're going in the same direction. Okay, with respect to the water and respect to the air, we want to find the bird's airspeed with respect to the air, how fast it's moving in respect to the wind. Okay, so because the wind is moving, okay, the wind is moving at 23 miles an hour, and it says that the regular speed of the bird is 35 meters per second. The wind is going 23, which means the bird only has to create 12 meters per second of speed. Okay, so it doesn't have to work as hard. Okay, now if the wind decreases, the bird is going to have to generate more speed to keep that speed. Okay, so we're looking at how speeds add and subtract to each other. Okay, now if we look at this, so the bird looks like it's going 35 miles per hour if you're like sitting in the water. Okay, but the bird only has to do 12 meters per second of speed on its own because the wind is producing 23 meters per second of speed. Okay, now if we look at an airplane going at an angle, flying, all right. So Cleveland's about 300 miles east of Chicago. A plane leaves Chicago flying due east at 500 miles per hour. The pilot forgot to check the weather and doesn't know that the wind is blowing to the south at 100 miles per hour. What's the plane's velocity relative to the ground? Okay, so we have the two vectors. We have The straight line vector, which we know is 500 miles per hour east, but the wind is blowing 100 miles an hour south. So this vector right here, this resultant vector, is the actual velocity relative to the ground, a combination of these two, okay, of the straight line speed and the wind speed. It's blowing them out at an angle of a different speed. Okay, so kind of think about how to do this. You have one leg, you have the other leg. You can figure out the hypotenuse by just using the Pythagorean theorem. Okay. All right. So the initial speed, 500 squared plus 100 squared. So the initial airplane speed is 500 miles per hour. The wind was 100 miles an hour. So your angled speed is 510 miles per hour. But we also want to figure out the angle that it moves. So we know the two sides of the triangle. We can use the tangent. Tangent of this angle is opposite over adjacent. Okay, so 100 divided by 500. Inverse tangent of that gets you 11 degrees. Okay, so the velocity of the new plane of the plane relative to the ground now, instead of 500 miles per hour due east, it's 510 miles an hour at an angle of 11 degrees south of east. So 0 degrees east, or 0 degrees south of east is due east. So it actually drops 11 degrees south. Okay. Now those are all the information for this section. Make sure you look at and do the formative assessment and ask questions as needed at the bottom of the form, and we'll see you in class.